Hi class, how are y'all doing today? Um, I hope y'all are doing well. So we're kind of in a weird situation, obviously. Normally you'd be in class and I'd be lecturing either over a PowerPoint or writing some stuff on the board. Here we're kind of confined to just recording myself and me kind of walking you through the PowerPoint. I'm going to try to get a little bit better technology to maybe there's a thing called an Elmo that'll allow me to write and you see what I'm writing at my desk. Hopefully that'll help. But for now, for this chapter, maybe just the first few sections, we'll just stick with this, and hopefully this will help some of y'all along the way in y'all's assignments. So probably the best thing you can do is pull up the PowerPoint, maybe print it out, have it handy so you could look at it at the same time as I'm looking at it. Writing notes is always good too. So if there's some points that maybe the PowerPoint don't show, and I bring it up and I tell you, you should probably write it down. Go ahead and write it down. So I guess we should just get started. You just took a test on Chapter 5. We did that online. Hopefully that went okay. If you struggle with something or you're still not sure about something, just send me an email. But in this chapter, we're going to talk about what are called confidence intervals. Okay, and so confidence intervals, the idea is you have some population parameter that you're trying to get a hold of. Very rarely can you actually measure an entire population. And that's why stats exist in the first place. You have some population and you want to get to know something about them, and usually it's something like a proportion or an average. The mean is almost always what you're looking for. This is what any drug company, in the nursing field, big businesses, this is how they decide, and this is how they make decisions, is based on this idea of what the mean is. Very rarely can you measure it, and so we take samples, which we've talked about before. Usually try to take the samples in a way that is not biased or unbiased. You do this by putting some kind of randomness in it. And so what we're really looking at here is how do we get a really good guess at a population parameter, and that's what a confidence interval is for. It gives us a confidence level. It gives us, okay, we're confident to some degree that this population parameter will be in here some amount of the time. That's kind of what we're looking at here, just in layman's terms. We'll get into more specific lingo in just a second. But for 6.1 here, we're looking at confidence intervals for the mean. So we're trying to get a hold of a population parameter, mu, the mean, where the standard deviation is something that's known. In 6.2, we'll do the same thing, but sigma is not known. It's unknown. And so our calculations will change a little bit, but the idea is still kind of the same. 6.3, we're trying to get a hold of a proportion, so a population proportion. Rather than a mean. And this could be useful in many cases, and so we'll look at that when we get there. In 6.4, I think we may go past this section because we're already kind of running out of time. I want to kind of hit the high points of all these chapters. So 6.4, I think we maybe can gloss over and kind of just get out of the way. Okay. So if we're looking at 6.1 here, kind of the objectives, we want to find what's called a point estimate and a margin of error. So a point estimate is just a very simple, straightforward guess as to what the population parameter is, in this case, the mean. We want to look at how to construct and interpret, this is very important, how to interpret a confidence interval for the population mean when sigma is known. Confidence intervals are things that are used widely throughout the world and in any business, or especially the thing that keeps coming up to my mind is medical studies. They kind of give you this with 95% confidence that the drug works, or that the mean 95% confidence that the mean weight loss is this or that, things of that nature. You got to be very careful because confidence intervals can be misconstrued. These people doing these studies can use terminology in such a way that can be very misleading. lastly, the objective here is to determine the minimum sample size required when estimating a population mean. Generally, the larger the sample size, the better. We'll kind of have a minimum for that that we'll look at. Okay, so a point estimate for population mu, that's what that is. That this here mu, it's that the Greek letter mu, it means mean. We've talked about this before. Population mean specifically. A point estimate is a single value estimate for a population parameter. So again, it's a very straightforward, our best guess. Boom, there it is. There's a number right in front of you. That's our best guess for the population mean, or any population parameter at that. And so when we kind of try to come up with these estimates, we want to obviously have some logic behind them. And it turns out mathematically that the most unbiased, so we try to aim to not be biased in our estimate. We could, in this class, we're not going to go very much into what it means to be biased. Just think of it as you don't want your own, your thoughts, your feelings, or what you want to happen to affect whatever you're trying to prove or disprove. And so in order to do this, we have to look at things that are unbiased. So we try to aim to be as unbiased as possible. Very rarely in the real world can we be completely unbiased, but we try to minimize bias. And it turns out in this case, the most unbiased, according to statistics and other stuff that we're not going to talk about here, just trust me, is the most unbiased point estimate of the population mean, sigma, x bar is. So what we think of as mean, add them all up, divide by the sample size, or n, lowercase n, turns out is the most unbiased point estimate of mu, the population mean, which is very useful for us. There's no weird calculations really going on. It's pretty straightforward, something you've known for a long time. So our best guess at the population mean mu is the sample mean x bar. That sample statistic. It's just a straightforward calculation. Add them all up, divide by how many there were. Okay, and so we have a little graph here that kind of shows this. If we want to estimate mu, we use x bar. Okay. So let's look at an example. So a researcher is collecting data about a college athletic conference and its student athletes. A random sample of 40 student athletes is selected, and their number of hours spent on required athletic activities for 1 week are reported. Okay, pretty straightforward. Find a point estimate for the population mean mu, the mean number of hours spent on required athletic activities by all student athletes in the conference. Okay, so it's very straightforward here. We have some population. The population here would be maybe all student athletes, or maybe all student athletes in this athletic conference. I don't know, but you can kind of get the idea. It'd be almost, I wouldn't say it's impossible, but almost a little unrealistic to go around and try to actually figure out the number of hours spent on athletic activities for 1 week for every student athlete in like a conference. And so what we do is we take a sample. We try to be very careful about how we pick the sample so we don't introduce bias. We do this by simple random sampling. We've talked about this before. Again, a point estimate is our very straightforward, basic, what's our best guess? And it turns out for the population mean, our best guess for that, if we can't actually calculate it, is x bar. So you just calculate it. You add them all up, divide by how many there are. So what you'll do here is you will take the number of hours, you will add up all the number of hours here, and you'll divide by how many there were, which they just told us. It's 40. So 40 student athletes. So add them all up, divide by 40, and you should get the most unbiased estimator for the population mean. And this is our best point estimate that we can make. And so here we go. Add them all up, divide by how many there were, and we get 21.1. Fairly straightforward, not too complicated. And so we say the point estimate for the mean number of hours spent on required athletic activities by all student athletes in the conference is about 21.1 hours, which is believable. Obviously, the larger the sample size gets, the better our estimator becomes. And as sample size increases, it gets better and better until you actually reach the whole population. It's exactly what you would think would happen. Okay. Okay, so another thing we're going to look at we have point estimates. These are our best guesses if we don't want to do much calculation. Unfortunately, there are some flaws to it. Very rarely are you going to make the guess exactly right. You may be close, but you're more than likely not going to be right on the spot for what the actual population mean is, or whatever parameter you're trying to calculate or get a good guess at. So what may be a better thing to do is to capture it in an interval, okay, and to find a probability and attach a probability to it. And so that's what an interval estimate is for, and that's where we're getting to this confidence interval idea. An interval estimate is an interval or range of values used to estimate a population parameter. Okay, it's exactly what you think, an interval from algebra. You're just taking, putting parentheses around these two numbers that are kind of your bounds of your interval, and you're saying that we kind of have an idea, we kind of think based on logic and statistics and probability that what we're trying to get a hold of, this population parameter, is in this interval, okay? So here what we're talking about is before finding a margin of error for an interval estimate, so this will give us an idea of how far off can we be. We first determine how confident we need to be that our interval estimate contains the population mean mu. So we need to come up with a confidence. How confident do we need to be? Obviously, if we want to be 100% confident or really close to it, we just make the interval really big. Now, how useful is this? I don't know. What we want to do is make the interval really small and yet still have a high level of confidence. Obviously, this starts to happen whenever n gets large. As your sample gets really close to the actual number of individuals or data in the population, the better your calculation is going to be for your point estimate, and the better your calculation will be for your interval estimate. Your interval should shrink. But again, we'll talk about margin of error in a second. But what it comes down to is we need to know how confident we need to be before we determine this interval. Okay, so level of confidence. So we use lowercase c to denote this. What we're looking at here is the level of confidence is the probability that the interval estimate contains the population parameter, assuming that the estimation process is repeated a large number of times. Okay, this is very important here. This isn't the probability of it being in there. That's not what this is saying. The level of confidence is telling us the probability that our estimate, our interval estimate, will contain the population parameter if we keep repeating this process over and over. That's what we're essentially saying. And we'll get further into this in a second when we start calculating things. We're kind of just looking at the semantics right now. Critical values are the way we determine confidence and how we numerically calculate and find the bounds of our confidence intervals. Critical values are values that separate sample statistics that are probable from sample statistics that are improbable or unusual. Okay, so anything outside of these critical values we consider improbable or unusual. We've talked about before, things are unusual. We consider events unusual if they happen less than 5% of the time. We'll kind of look at something similar here, and we'll bring back the normal table and the normal distribution and your z-scores, and all of that will come back here very soon, actually. Okay, and so for instance, if our confidence level is 90%, we have to determine what these critical values are, and so this is a very good representation of the critical values. If you look here, our confidence level is the area, okay? We want 90% of the area. Notice how we're symmetric here. We want our interval to be symmetric around some value. It'll actually be a point estimate. And so what do we have to do? Well, we say C is our confidence level. It's the area in the blue region. So here's your confidence level. Again, remember, area is probability in statistics. You want to think of area under a curve as probability. It has substance. The more area there is there, the more probability there is there. Now, whether or not that actually means the probability of something occurring, that has to do with context. But just it's okay to think of area as probability. The area in the yellow regions are what's left over. Obviously, if you add up all the area under a PDF, a curve, here in this case it's a normal curve, it must all add up to 1. We know this. All possible events, the probability of these events occurring has to add up to 1. This is a continuous distribution. So unlike the discrete where we can just add up all the probabilities, it's a little weird. We have to look at area, but it's the same idea. We add up all the area under the curve, we should get 1. And so if we take that idea that all the area under the curve is 1, so if we add up all of this area, it should add up to 1, but we know this area here is C. In this case, we say 90%. 1 minus C should be how much area is left. And so because we're symmetric here, very nice things happen because of the normal distribution, because it's symmetric. These two areas here must share what's left evenly. Okay, they must because of the symmetry. And so if we have this 0.10 here is left for both of these, half of this must go to each of these yellow regions here. And so if we do this 1/2, 1 minus C, this is all this is saying. It's saying, okay, we have 0.9 as our confidence level. 1 minus 0.9 is what's left, what can be distributed on both sides of the this normal distribution. If we have that, that should be what is on each side, which is 0.05 here. And we look for this critical value, okay, on our normal table. We look for this critical value. We look for, on our normal table, we look for the area corresponding to 0.05. Remember, we've done problems like this before where you were given a normal distribution like this, and you were to look for these z values corresponding to an area. This was a very specific type of problem that some of y'all struggled with, which is okay. It is a little confusing, and this is the only time you can actually do this type of problem is if you have the symmetry, and you will here. You'll have this area here. This area here is saying, we're saying is 0.05. So you'll look at your normal table, and on that normal table you look for 0.05, because remember the normal table gives you the z value corresponding to area to the left, which I guess on here is to the right of how you're looking at me, but if you look at the screen here, to the left of the z value. And so if you look at your normal table, you will get a z value of negative 1.645. This is the critical value. Critical values are z values. They're the same thing. They're just z values we're using in a very specific way. Because we know the critical value here, we actually know the other because of symmetry. It's actually just the positive of that z-score, which is 1.645. Okay. So we're going to kind of start looking at different levels of confidence. So here we're going to look at this 90% confidence interval. So we want 90% level of confidence. If the level of confidence is 90%, this means that we are 90% confident that the interval contains the population mean mu. We are 90% confident. This is very important you interpret this correctly. We are 90% confident. There's a difference between confidence and probability. You do use probability to help find like the confidence interval, but confidence and probability are different. We are 90% confident that the interval contains the population mean mu. Okay, we are 90% confident that the interval contains the population mean mu. And we'll have different confidence levels that we'll look at, and it just depends on what your situation is and what you're trying to calculate. And so here we go. This is what we just calculated. The corresponding z-scores are plus or minus 1.645. And that'll always happen. It'll always be the plus or the minus because we are centered around, here it's z equals 0, but we'll find a way to remember if you were given a distribution, you always can convert it, any normal anyways, any normal distribution, you can always convert it to a standard normal. And so that's what we'll end up doing. In the case of finding our bounds for our confidence intervals. Okay, so what is sampling error? Our sampling error is the difference between the point estimate and the actual population parameter value. Okay, the difference between the point estimate and the actual population parameter value. So we have a point estimate. It's just add them all up, divide by how many there are. That's our unbiased estimator for mu. And we have some population parameter value in the ether. We don't know it. We don't know how to calculate it, but maybe eventually it's feasible to get a hold of it. Sampling error is the difference between what your point estimate guess was and what the actual population parameter is. For mu, the sampling error is the difference between x bar and mu. This may look really familiar, hopefully. We did some things like finding the probability that a sample mean is less than whatever. We did something similar to this. We did x bar minus mu sub x bar, which was the same as mu for sampling distribution, divided by sigma over root n. So this should look very familiar. So actually in your numerator, you were calculating a sampling error. Obviously, mu is generally unknown. That's the whole point of this whole process is mu is unknown. We want to get a hold of it. And x bar varies from sample to sample. So for every sample we get, x bar is more likely going to change. And we'll keep taking samples, more and more samples. The more and more samples we do, and our results are the same on each one of those samples in terms of our calculations, the better evidence we have to support whatever we're trying to prove. Obviously, as lowercase n, the sample size increases, the better our estimates are going to be for mu. But obviously, our goal is to reduce sampling error. We want to reduce any type of error if we can. Okay, so margin of error, a different type of error. It's sometimes called the maximum error of estimate or the error tolerance. The margin of error is the greatest possible distance between the point estimate and the value of the parameter it is estimating. It is denoted by E, capital E specifically. It turns out in this case, capital E is this critical value, this Z sub C that we calculated before based on our confidence, times sigma of x bar. So if you remember that sigma of x bar, that is the standard deviation of a sampling distribution of means, right? It's a standard deviation of a distribution of means. And it's very straightforward. It's the Z critical value, which you've already calculated before you even get to this part. You have to figure this thing out. You have to figure out how confident am I, and what critical value does that confidence give me before you can even move on, before you can do anything like this. But once you have that, you're kind of home free, because first you can calculate this margin of error. We can actually do it all together in just a second, but you can actually calculate margin of error. And so if they ask for margin of error, you're actually just calculating a part of the confidence interval, which we'll get to that in a second. So we have this critical value, which is just a Z value that you find on your normal table, times sigma, which is the population standard deviation. Now remember, in this section, the population standard deviation is known. Okay, if it's not known, things are going to change. But in this section, it is known, so let's use it. So we have sigma over the square root of n, where n is the sample size of each of the samples, which we've seen this before. So the Z value, this critical value, times sigma over root n will be our margin of error, our capital E. In order to do this, there are two things that must be true. The sample must be random, which we always do this anyways because we don't want bias in our sample. And then what we're trying to do, we try to limit bias as much as possible, and randomness helps eliminate bias quite a bit. Also, the population must be normally distributed. Or n has to be greater than or equal to 30. So we already seen this before with sampling distributions. If the original distribution was normal, then it actually didn't matter what the sample size was. You could do this calculation and be about your way. You could calculate the mean of the sampling distribution of means, and that was just the same as the population mean. and you could calculate the standard deviation of the sampling distribution. That's sigma sub x bar, like right here. You could calculate this thing and just use the population standard deviation divided by the square root of n. And if you knew the original population was normally distributed, sample size didn't matter. But what's really nice about the central limit theorem and all of this niceness with normality is if n is greater than or equal to 30 here, if your sample size is large enough, it doesn't even matter what the distribution of the population is. You can still do this calculation, which is kind of the beauty of all of this. And that's the reason we want sample sizes to be as large as possible. Now, sometimes we can't do that, and there are ways to get around that. I don't know if we'll talk about it in this class. We may at the very end if we have time. But usually we want to work with things where sample sizes are large. So let's find the margin of error. So we want to use the data in example 1, and we want to kind of construct a 95% confidence level. So we're kind of work into this confidence interval idea by first calculating the margin of error. You have to do that in order to calculate a confidence interval or to construct one. You have to calculate the margin of error. So let's just look at that first. So we want to use the data in example 1, and we want to construct a 95% confidence level or confidence interval to find the margin of error for the mean number of hours spent on required athletic activities by all student athletes in the conference. And we want to assume the population standard deviation is 2.3 hours. So we want to assume that we know the population standard deviation. That is key for this section. We can't do what we're about to do if we don't already know the population standard deviation, and we do. And so let's go through this. Let's kind of walk through the example. Because sigma is known, the sample is random. That was in the example from before. And n is 40, which is greater than or equal to 30. We can actually just use the formula to calculate the margin of error. So the first thing is to calculate that z value. Okay, if you remember before, let's go back real quick. I'm probably going to go way too far. There we go. So in this case, C was 0.9, and in our case now, C is 0.95. So we're going to look for this value here. You're doing the same thing we did here. We're going to do 1 minus 0.95. So if we go back, we're going to do 1 minus 0.95. And then we know that has to be evenly distributed on both sides of the normal, and we look for the z-score that corresponds to an area of 1 minus 0.95 divided by 2, which is 0.025. And so we look for this this z value, and it is 1.96. So we have that negative 1.96 and 1.96. So when we do what we just did there, where we look for the area corresponding to 0.025, you're going to get a value of negative 1.96. But the positive of that is z sub c, this critical value. And so you can look at your normal table if you want. Maybe that'll help make the connection there. But you'll be looking at your normal table for 0.025. And by doing that, you'll find this z sub c, this critical value that we need. And so here we go. They have this normal curve, 0.95. Here's all the area in the middle. 1 minus 0.95 will be the area that's left over that has to be evenly distributed between both sides of this normal. And so if we look at this area here of 0.025, we kind of work backwards. We kind of do it, we look at our normal table and we go backwards. We look for the area of 0.025 and look for that z value that corresponds to it. And in this case, the z value is negative 1.96, and so z sub c is 1.96. Okay, so using z sub c is 1.96, sigma is 2.3, and n equals 40, we can do this whole calculation. It's a very straightforward calculation, though. I guess the hard part is remembering the formula, maybe. But it shouldn't be too bad, especially on this first homework that you're going to do over it. So we are 95% confident that the margin of error for the population mean is about 0.7 hours. Okay, so now let's actually get to the big thing here. We actually want to calculate a confidence interval for the population mean. So a C confidence level, if we have a C confidence level, A C confidence interval for a population mean mu. Remember, we're trying to get an idea of what the heck is mu. We have this point estimate, which usually they aren't that good, because very rarely are we going to be right on what we need to be. So let's put it in an interval. So we had this idea, we're going to create this interval based on confidence, and we have this margin of error idea. It turns out that the confidence level, or the confidence with a confidence level of C, the confidence interval is X bar, our point estimate, minus the margin of error, is less than mu. So mu is greater than this lower bound, and mu is less than X bar plus our margin of error. So mu is caught between this lower bound and this upper bound, where the lower bound is the point estimate minus the margin of error, and the upper bound is the point estimate X bar plus our margin of error, which is here. And to calculate the margin of error, we just talked about that. Okay, so the probability that the confidence interval contains mu is C, assuming that the estimation process is repeated a large number of times. Okay, that's kind of a key fact there too. This estimation process has to be repeated many, many times before this confidence interval actually makes sense. Okay, so in words, let's kind of just try to, we'll cut it off after this, and I'll put another video up. This is actually a really good stopping point. So to construct a confidence interval for mu, when sigma is known, we verify that sigma is known. It'll be clear. The sample is random, and either the population is already normal or n is greater than or equal to 30. We find the sample statistics n and x bar. Okay, x bar is really easy to calculate. This is our point estimate for mu. We find the critical value. So we look at our, how confident do we want to be? We look for that corresponding z sub c, doing what we've done before already, using a normal table. We find the margin of error. This is E equals z sub c, that z value, times sigma over root n. Remember, sigma has to be known, otherwise this doesn't make sense. And we find the left and right endpoints and form the confidence interval. The left endpoint is x bar minus E, the right endpoint is x bar plus E, and the interval is x bar minus E is less than mu, is less than x bar plus E. And so we have this bound for mu. Rather than just having a single guess what mu is, we have a bound for it. We have caught it in this interval, and there's some kind of, it's not probability, but confidence attached to it. And the way we find this confidence is using probability, if that makes sense. It's the best we can do, because if we can't actually measure a population parameter, if we can't actually go out and calculate what mu actually is, we're going to have to estimate. And when we estimate, there's going to be a potential to be wrong in our estimate. That's just the way it is. It's the way statistics works. But we try our best to make a really educated guess, and confidence intervals are kind of the go-to way for getting a good guess at what mu is. Okay, and so I'll put out a part 2 tomorrow for this video, and what I'm assuming is this next one will be an example of actually constructing a confidence interval, which it is, and we'll start there again tomorrow. If you have any questions, just send me an email, and have a good rest of your day.